Hey everyone, we're going to make a quick video on the mean value theorem, a more general version of Rolle's theorem. We're going to start by motivating the mean value theorem by recalling the average velocity of a function f on a closed interval a to b. Remember that that's the slope of the secant line from a to b, which is f of b minus f of a all over b minus a. And remember that the picture associated with this, something like this, right? We've got our axes, and we've got some values a and b, right? X values, and maybe this is f of a. We're just going to assume this function's increasing, but it could be decreasing, for all we know. And maybe we'll make our points right here. And perhaps our function does something like that. This is y equals f of x. And our secant line, perhaps I'll use this, is this line right here. Right? Again, it's the line connecting a comma f of a and b comma f of b. Now remember, the secant line of f on a to b has slope equal to the rise over the run. F of b minus f of a all over b minus a. Okay? So what we're going to do is we're going to cite the mean value theorem. This is a theorem whose statement and name you need to know. And it's going to tell us something about a function and its derivative and relate it to the average velocity of the function on the interval a to b. This says that if a function f is continuous on the closed interval a to b, just like with Rolle's theorem, and differentiable on the open interval from a to b, again, just like Rolle's theorem, but that's it. Those are the only two conditions. We just have the continuous and the differentiable. Then there's some c in the open interval a to b, such that f prime of c equals, you guessed it, f of b minus f of a all over b minus a. So what this is saying, if we can go ahead and copy this picture right here, is that somewhere, at some point C, it looks like it might be around, I don't know, there or so, roughly. The tangent line to the function f of x is parallel to the secant line of f. So I'm just going to write here f prime of c equals f of b minus f of a all over b minus all over b minus a. Okay. So that's what the mean value theorem says. So again, you might notice that when f of a equals f of b, this is just Rolle's theorem, right? It's going to equal 0. But this is also a more general version because we don't require that f of a equals f of b. Let's take a look at an example of when we might use the mean value theorem. So here's a classic example. You can find this video on YouTube. There's a situation where a driver passes a certain mile marker on a road, and then 2 hours later, they pass another mile marker, or perhaps it's a checkpoint, and the police officer pulls them over and gives them a ticket. And I say, you were speeding at some point during those 2 hours. And they say, well, how do you know? And the officer says, well, look, you traveled 160 miles in 2 hours. You were averaging 80 miles an hour. And I say, yeah, but how do you know that I was actually ever speeding? And the officer says, well, by the mean value theorem. So let's take a look at what's going on. We'll start at time 0 at mile marker 100. Then, again, this graph is not going to be to scale here. Maybe if you want to think about it in terms of minutes, then you can. So we start here, right, at 0, 100. After 2 hours, we're at mile marker 160, right? Maybe this is miles. This is hours. Okay? And maybe we'll say that we drove something like this. I don't know. Okay. Well, the officer again pulls us aside and says, look, your average speed was f of 2 minus f of 0 all over 2 minus 0, which is 260 minus 100 all over 2 minus 0, which is 80. That's speeding. Speed limit is 65 miles an hour, right? And you say, well, hey, you don't actually know that I was ever speeding at any one point. The officer says, yes, well, actually, by the mean value theorem, there's some value c. I'm not exactly sure where it was, but sometime between 0 and 2 hours, sometime in the last 2 hours, that you were actually going 80 miles an hour. (80 miles per hour). All right. Now let's write this up a little bit more formally. We're going to say let x equal the number of hours since passing mile marker 100. Let's just block this off. What? Okay. Let f of x equal mile at time x, right? So the mile marker, so to speak. All right, so what we're saying, so this, I think it's clear here that the way that we drive, the way reality and time work and distance work, is that f is a continuous and differentiable function. So f is continuous on 0 to 2 and differentiable, right? We can talk about the car's velocity at any point, right? Provided there are no sudden breaks in their speed or something crazy like that. Provided they don't get into a crash or, I don't know, hit a pothole that alters their speed or something very weird like that. Okay? So we can talk about f as a continuous and differentiable function. So by the mean value theorem, which we call the MVT because I'm not going to write mean value theorem every time, there's some value c in the interval from 0 to 2 such that f prime of c equals f of 2 minus f of 0 all over 2 minus 0. And again, we know that that's 80 miles per hour. So, at some point, at some time, I'll say, between 0 and 2 hours, the driver reached 80 miles per hour. Okay. So that's how you do that problem. Now, example 7, this is a bit trickier. Just want to point out, I'm going to leave this for you to do in class, but the one thing I do want to point out is that based on what's given, we know f is continuous and differentiable, apparently on negative infinity to infinity, right? Because it says for all x. So we can use the MVT at some point, the mean value theorem at some point, right? What we're trying to do is we're trying to get this lower and upper bound for f of 8 minus f of 2. So think about how the given information might help you. And that's something that you're going to do in class. Or try it before class and ask me afterwards. And I will stop there.